Sections 6.2 and 6.3 were all about finding the volumes of solids. Now we're going to find the surface area of solids, and specifically solids of revolution. So we're finding the surface area of a solid of revolution. So like the area of the lampshade, or the things that look like trumpets, or whatever we made back in chapter 6. So we take a curve and we rotate it around an axis, and it creates a figure, and we're finding the surface area of the outside of that figure. Last time we were finding the volume of what was inside of the region. So here's, if we just had a sheet of paper and we unfurled it, then the surface area is just a rectangle. But we have curvy things, so it's not so simple. So we think about a cone. And if we undo a cone, then it depends upon the angle of the cone. I'm not going to go through all of the steps. It's rotated about the axis. We divide it up just like we did, and you can look at the proof in the textbook, but what really helps me to memorize it is really just that pi r h, the area of a cylinder. So the surface area of a cylinder. So 2 pi times the radius times the height. Imagine dividing it up into lots of little pieces. You need 2 pi times the radius. And then for the height, because it's curvy, instead of just a number here, we have that formula that we just learned for arc length. So it's going to be 2 pi times the radius times our formula for arc length. And there it is. You can do it with respect to x or with respect to y. That's one of the friendly things about surface area. It doesn't matter whether you measure with respect to x or with respect to y, just like arc length didn't. Do whatever is easier. The important thing is to make sure you have the right thing for your radius. So we'll go through and do some. Let's look at example 1. Y equals the square root of 4 minus x squared. So that's part of a circle. We have something that looks kind of like a wheel. Example 1, we have y equals square root of 4 minus x squared less than or equal to x is less than or equal to 1. And like I said, it's the arc of the circle, x squared plus y squared equals 4. And we're rotating at about the x-axis. I like to draw these things, so I'm going to make myself a set of axes. X goes from -1 to 1, and I know this is the circle with radius 4 centered at the origin, so I'm going to call this 1, 2, 3, 4. It looks something like that. We're revolving around the x-axis, so I get something that looks kind of like that, except not really, because that's a terrible picture. But I can see that this is my radius. My radius is the distance from the x-axis to the line. So my radius is equal to y, which everything's in terms of x's here. I want to integrate with respect to x. So my radius is going to be the square root of 4 minus x squared. Now I'm going to do the arc length part. So I will do dy dx is equal to 1/2 of 4 minus x squared. Subtract 1 from the exponent. Multiply by the derivative of the inside function. So that cancels with that. Leaves me with an x sitting on top of the square root of 4 minus x squared. I'm going to go ahead and square this and add 1. I'll do that in one step. Equals 1 plus x squared. And when I square the square root, it just disappears. So common denominator would give me 4 minus x squared over 4 minus x squared plus x squared over 4 minus x squared, which leaves me with 4 over 4 minus x squared. So 1 plus my derivative squared. My derivative squared simplified quite nicely. X squared, square root of 4 minus x squared. The radical goes away. 1 is 4 minus x squared over 4 minus x squared. And then minus x squared over 4 minus x squared. So those disappear. So my surface area is going from minus 1 to 1. 2 pi times the radius times the arc length part, which is oh wow, I could bring everything under one radical here. This is the integral from -1 to 1. You could pull 2 pi out in front if you wanted to, but when everything's underneath one radical, we have 4 minus x squared times 4 sitting on top of 4 minus x squared dx. So we're really just going from -1 to 1, 2 pi times the square root of 4. So 2 times 2 is 4 pi, and we're going from -1 minus -1, so 8 pi. And there's the pretty answer. Easy. Let's do another one. I'm going to take a minute and set it up for us. Now, I did peek at the example in the book to figure out what the graph looked like, but what if I didn't have that there? Well, I could have just plugged in 2/3 times 3 to the 3/2 power. I know that when y is equal to 0, x is equal to 0. When y is equal to 3 at the other end, x is going to be equal to about 3.46. So I have an idea what it looks like. Even if it had gone that way instead, it wouldn't matter for what I need, because what I need is to figure out where my radius is. Since I'm going about the x-axis, here's my radius. Radius is equal to y. This time, I want to integrate with respect to y. So I don't have to put a function value in. I'll just put in y for my radius. Now, I need to do the arc length part. For that, I need the derivative of x with respect to y. 2/3 is hanging out. 3/2 falls down. y2 subtract 1 from the exponent. Ooh, I like that. That all cancels away. I'm just left with the square root of y. So 1 plus dx dy squared. Write that upside down. Dx dy squared is 1 plus y to the 1/2 squared, which is 1 plus y. Easy enough. So now my surface area, I'm going from y equals 0 to y equals 3. 2 pi times the radius, which is y, times the arc length, which is square root of 1 minus y. You could do some integration by parts. I would probably just let u equal 1 plus y. Then du is dy, and y is equal to u minus 1. U at 0, let's say u of 0, is equal to 0 plus 1, and u evaluated at 3 is 3 plus 1, which is 4. So this is the integral from 1 to 4, 2 pi. Instead of y, I have u minus 1. And instead of square root of 1 plus y, I have u to the 1/2. It's one of those double subs. Integral from 1 to 4, 2 pi. I have u to the 3/2 minus u to the 1/2 du, 2 pi, add 1 to the exponent, divide by the new exponent, add 1 to the exponent, divide by the new exponent, evaluate from 1 to 4, and you end up with 232 over 15 times pi. That's easy. You just have to plug numbers in. Let's do another one. I'll take a minute and set this one up for us. This one's a little different. We're going about the y-axis. So this one I did have a pretty good idea what it looks like because it's just a happy parabola. And we're looking at from 1, 1 to 2, 4. And we're going around the y-axis. So my radius is equal to x. So if I'm integrating with respect to x, then r is just equal to x. dy dx is 2x, so 1 plus dy dx squared would be 1 plus 4x squared. So the surface area would be the integral from x coordinate 1 to x coordinate 2, 2 pi times the radius times the arc length, 1 plus 4x squared dx. And you get something that you can easily use u substitution on. U would be equal to 1 plus 4x squared. Du would be equal to 8x dx. U evaluated at 1 would be 1 plus 4. U evaluated at 2 would be 1 plus 4 times 4. So we would have the integral from 5 to 17 to pi x u to the 1/2 power du on top of 8x. So let's go ahead and pull 2 over 8, which is 4. So pi over 4 out front. And we have 2 pi u to the 1/2 du. We don't have the 2 pi. I pulled it out in front. We just have u to the 1/2 du. So pi over 4. Add 1 to the exponent. Divide by the new exponent. Evaluate from 3 to 17, and we end up with pi over 6 and square root of 17. 17 square root of 17 minus 5 root of 5. Okay, so we could do this both ways. Let's go through and do it by integrating with respect to y instead of respect to x. Now, if we wanted to do that, we're going to need to rewrite x is equal to y to the 1/2 power. My radius is equal to x, which is y to the 1/2 power. Now I need dx dy, which would be 1/2 y to the minus 1/2 power, which is 1 over 2 times the square root of y. And then 1 plus dx dy squared would be equal to 1 plus 1 over 4y. I'm going to kind of copy some stuff and flip my page over. So I copied our radius, our endpoints, and our 1 plus dx dy squared. So surface area is equal to the integral from y coordinate to y coordinate. So 1 to 4, 2 pi times the radius, which is square root of y, times the arc length portion, which is 4y plus 1 over 4y. I just got a least common denominator there and combined it into one term. You didn't have to. You certainly could have done it without doing that. 2 pi is still hanging out. I'm going to put everybody underneath one radical. So then we would have y times 4y plus 1 over 4y. Well, that cancels with that. We still have 2 pi. We have square root of 4y plus 1 on top, square root of 4 down below, so really 2 and square root of 4 can cancel away. So we have pi times integral from 1 to 2 square root of 4y plus 1. And now I'm going to let u be equal to 4y plus 1. du is 4 dy. U evaluated at 1 is equal to 1 plus 4 is 5. U evaluated at 4, because that should be 4, that should be 4, that should be 4, because we look at the y coordinates. U evaluated at 4 would be 4 times 4 plus 1, which is 16 plus 1, which is 17. So we have pi evaluated from 5 to 17 u to the 1/2 du, which is pi times u to the 3/2 over 3/2 evaluated from 5 to 17. And let's see, we end up with the exact same thing, except I've lost, oh no, we have it in there. Because when we plug things in, we end up with 2 on top and 3 on the bottom, and we have to get a common denominator. So we do end up with the exact same thing. Okay. Try practice number 1 on your own. We'll come back and compare answers. Before you get going, I did have to go back and find my error. Remember here, du was equal to 4 dy, so I needed an over 4 here in front. And that way we do end up with the exact same answer, just like we should. Now, do practice number 1. I had to give you limits of integration, so we're going from the point 0, 1 to the point 1, 0. Let me show you what this looks like. This is the entire graph. It looks like this weird little diamond shape. So you're going to end up with kind of a tent, finding the surface area of that little tent as it's revolved around the axis. So give it a try. We'll come back and compare answers. Okay, I did it both ways. Integrating with respect to x was much easier than integrating with respect to y, but I did get the same answer. So we're going from x equals 0 to x equals 1, revolving around the y-axis. So my radius is equal to x. I had to rewrite y is equal to, I subtracted x to the 2/3 from each side, and then raised each side to the 3/2 power to isolate my y in terms of x. I took the derivative. Exponent fell down, subtract 1 from the exponent. Don't forget the chain rule. I ended up with a negative thing, but then when I squared it, the negative went away. I ended up with what was inside the radical over the denominator squared. I got a common denominator, and I ended up with a single term, which made me very happy, because then when I plugged it into my formula, integral from one x value to the other, 2 pi x square root of 1 plus the derivative squared, the arc length portion, just simplifies into x to the 2/3 power, and I get 6 pi over 5. Now, if I do it with respect to y, a lot of the work is duplicated because the derivative is the same thing. It just has y in it instead of x. But the radius is equal to x, so you have to put in x as a function of y for your radius. So I had to work a little harder to get my derivative here. Now you notice even though my points were from the point 0, 1 to 1, 0, I went from 0 to 1 both times because I'm integrating with respect to y, and we want to go from 0 to 1 with y also, which is important because when we come down here, we end up having to use substitute, and we eventually have to integrate from 1 to 0, but we do indeed come up with the exact same thing. Do it however it's easier. Example 3. Oh, we have an exponential. So we want to generate a surface by rotating y equals e to the x about the x-axis. So let's set that up. Easy to draw. We all know what e to the x looks like. Example 3. And we're going from 0 to 1, so I'm going to say it looks something like that, because we know it goes wee It starts at 1 and it increases. And we're going around the x-axis. So since we're going around the x-axis, my radius is equal to y, distance from the axis of rotation, to my curve, which is e to the x. And we're going from x equals 0 to 1. So let's integrate with respect to x. So my dy dx is e to the x. So 1 plus dy dx squared is 1 plus e to the 2x. So my surface area is the integral from 0 to 1, 2 pi e to the x times the square root of 1 plus e to the 2x dx. And again, we're going to need to use substitute. So let's let u be equal to, well, if I let it be equal to the entire thing underneath the radical, it's not going to work for me. So let's let u be equal to just e to the x. Then du is e to the x. U evaluated at 0 is 1, and u evaluated at 1 is e. So go ahead and pull 2 pi out. We'll go from 1 to e. We have e to the x times u to the 1/2. And then this would be du over e to the x. So cancel and cancel. And that's not what we have. We have 1 plus u to the 1/2 du over e to the x. Cancel, cancel. Okay. Let me go ahead and rewrite this here. Du over e to the x equals dx. So I replaced my dx with du over e to the x, and that got rid of that. So now I just have 1 plus u underneath that radical, and that's something u squared. I have 1 plus u squared underneath that radical. Now that's something I'm going to need trig sub for. So this one's a lot of skills in one problem. So u is equal to tan theta. Du is equal to secant squared of theta. So if 1 is equal to, actually, yeah, I think I'm going to just keep it and then I'll draw a triangle at the end. So I'm going to treat this as a indefinite integral, and then I'll bring my u's back. So we have 2 pi 1 plus tangent of theta squared to 1/2 times secant squared of theta d theta, which is 2 pi times the integral, and this becomes secant, so I end up with secant cubed of theta d theta, which is a loopy integral. And I'm going to go ahead and look at my answer here. Yeah, I get pi times secant cubed, and I end up having to use integration by parts, and then I have to bring everything back. I would not expect you to do this by hand on the test. If I gave you this problem, I would expect you to get to this and then plug it into your calculator and get an answer. So let's do a couple more practice problems. Try it on your own. We have y equals the square root of 5 minus x, and we're going about the x-axis. I only did this one way. I was given x's go from 3 to 5, so I just went ahead and stuck with integrating with respect to x. So my radius was equal to y because I was revolving about the x-axis. So I found my derivative, negative 1 over 2 times the square root of 5 minus x. I squared it and added 1. I ended up with 21 minus 4x over 4 times 5 minus x. I took the integral from x is 3 to x is 5. I multiplied r times the arc length portion. Then this 5 minus x canceled with that 5 minus x because it's really underneath the radical. Then I divided the square root and square root. So the square root of 4 is 2, which I canceled with that 2. And I ended up with just 21 minus 4x underneath the radical. So I made that my u. Then it became an integral from 9 to 1, instead of 3 to 5, because you always keep the limits of integration where they start. And it became negative because my du was negative 4 dx. So I ended up with negative pi over 4, u to the 3 halves over 3 halves, and you can see where it went from there. The last couple of practice ones, we're just going to set them up because that's the challenging part, is setting them up, and then after that, usually you'll just plug them into your calculator to get your answer. So the given curve is rotated about the x-axis. So again, rotating about the x-axis. We'll do this one together, then I'll leave you to do practice number 4 on your own. So x squared is equal to e to the y power. X squared e to the y power, and 1 less than or equal to x less than or equal to e. First, we want to do it with respect to x. So let's draw a little graph. I don't really know what this looks like, x squared equals e to the y, but I'm thinking it lives in the first quadrant, and x is going from 1 to e, and we're rotating about the x-axis. So the important thing that I need to know is that my radius is equal to y. Radius is equal to y. So if I want to do the first one, integrate with respect to x, I need functions with x's in them. So since x squared is equal to e to the y, I want to isolate y. So natural log of x squared is equal to the natural log of e to the y, which is just y. Well, I know the laws of logarithms. Y is equal to 2 times the natural log of x. Didn't have to do that, but you know, if you can, why not make your life easy by getting rid of exponents? So dy dx is equal to 2 times 1 over x. 2 over x. So 1 plus dy dx squared is 1 plus 4 over x squared. So my surface area is equal to, and I'm given my limits of integration because I have my x's, from 1 to e. 2 pi times the radius, which is y, which is 2 times the natural log of x, 2 natural log of x, times the square root of 1 plus 4 over x squared. And then I say, yay, I don't have to try to integrate that because it looks really ugly. You don't have to simplify stuff. You can leave it exactly like that. Number 2, we have x squared is equal to e to the y. So x is equal to e to the y to the 1/2 power, so square root both sides, which is e to the y over 2. So dx dy is equal to e to the y over 2 times 1/2. Don't forget the chain rule. dx dy. So 1 plus dx dy squared is equal to 1 plus e to the y over 2 squared, which would be 1 plus e to the y, because we multiply the exponents, over 4. Now I need to figure out my limits of integration. So 1 is less than x is less than e. And y is equal to 2 times the natural log of x. So that means when x is equal to 1, y evaluated at 1 would be 2 times the natural log of 1, which would be a big fat 0. And y evaluated at e would be 2 times the natural log of e, which is 2 times 1, which is 2. So my surface area is the integral from 0 to 2 pi times my radius, and my radius is just y. And then my arc length part, square root of, I've forgotten it already, 1 plus y, e to the y over 4. Now, I'm going to take a minute, plug this into Desmos, and then plug it into Symbolab and make sure I get the same answer. Feeling pretty good about myself right now. So first thing I did was I plugged in my function that I was given, x squared equals e to the y from 1 to e, to see what it looked like. And, you know, my little guesstimate was not at all right, but it didn't matter, because I knew that it lived in the first quadrant, and I was able to figure out that the radius was equal to y. So then I just looked at the f of x that I had calculated for a function of x, and yeah, it's perfect. It lives right there on top of that original function. So I did the integral from 1 to e of 2 pi times f of x, because that was my y, times the square root of 1 plus 4 over x squared, and I got 17.88, etc. Then I did the same thing for g of y, which was e to the y over 2. I got that one right too. And then this one was just the integral from 0 to 2 of 2 pi y times the square root. This was the arc length part, dx dy squared, and I still ended up with the same thing. So feeling pretty good about those. So you can check these to be sure you have them right. No, let's don't leave. Let's just minimize it. So try number 4 on your own, and we'll come back and compare answers. Okay, not too bad. We did have some inverse trig functions, but you didn't have to do the integration, so it's okay. I had y is equal to 1 plus sine of x, so this one I really did know what it looks like. It's just the sine wave shifted up 1, so it starts at 0 and goes up to 2 because pi over 2 is where sine is equal to 1, and 1 plus 1 is 2. Derivative of 1 plus sine is just cosine. So I didn't even bother to simplify anything here. I just plugged it all in. And I was given the limits of integration from 0 to pi over 2. Then I had to figure out a function for x in terms of y, because I want to set up the integral with y's in it. So y minus 1 is sine of x, so x is the inverse sine or arc sine of y minus 1. Derivative is 1 minus, the square root of 1 minus y minus 1 squared, and then the derivative of y minus 1 is just 1 sitting on top, and then I did 1 plus that derivative squared. If x is equal to 0, then y is equal to 1. If x is equal to pi halves, then y is equal to 2. And the worst part of this one is that I had to use a whole nother sheet of paper just to write down the answer. So 2 pi times your radius, which is x, and then your arc length part, which is the square root of 1 plus your derivative squared. And again, this time I went ahead and plugged it into Desmos, and I get the exact same answer both ways. So life is good, feeling good about myself, even though I didn't have to integrate those. So you can do these things. Just remember, do whatever is easiest. Even if you don't know exactly what your line looks like, if you're revolving around the y-axis, there, I'm going to write something else on this paper just so it's not just that one line. Rotate about the x-axis. Radius is equal to y. If you rotate about the y-axis, then your radius is equal to x. If you want to integrate with respect to y and your radius is equal to x, then you're going to have a function for your radius. If you want to integrate with respect to x and your radius is equal to x, then you just have x for your radius. So there's 4 different ways you could do these problems, depending upon how you want to integrate and which axis you're revolving about. You can do that.